I'm Fred. I work for a company called Recipe. We do a bunch of stuff, but one of our big things is clothing recommendation engines. And today I wanted to tell you about two problems that we'd had, two stories around these problems, like a performance problem, a memory problem, and kind of what we did about them. So this is not about 24. Is that even on anymore? And this is about a real-time recommender system. So if you build recommendation systems, you very often have this kind of gap. You have your batch predictions. This is the most accurate algorithm you can run, but it takes a long time to run. It might take, I don't know, 12, 24 hours or something to run. And you can only really run it on all of your users' data at one time. So it's great for accuracy, but not at all good for responding to what's actually happening. Then you have your real-time recommender, which is kind of, responds in real time to individual events as they come in, clicks, interactions, purchases, and so on. And you get something that's a bit more approximate, but which is changing literally every second in response to every single possible event. And obviously, we're greedy, and we want both of these things, so you combine them. And this is like not at all a new idea. So we thought, that sounds good. We should do that. And we did. So what went wrong? Well, it was fine until we deployed it. There's a PR that looked good. I thought, I approved it. It worked fine in our staging environments. We also have these kind of these evaluation tests where we kind of predict what is the improvement in accuracy that we're going to get on real data. Those numbers were really good. And actually, for the first 12 hours after we deployed it, it was really good as well. Then around that evening, kind of this thing happened. So that blue line, which starts kicking up about 7 p.m., that's the number of jobs in a queue, or the backlog of jobs in a queue, and it kind of goes up to about 10,000 jobs. The red line is the number of instances that are processing that queue. So we're kind of adding new instances, and it's not really doing anything. It does eventually come back down around 11 p.m. That's not us rolling back the change or fixing anything. That's just another user going to sleep. So yeah, we've got a real-time recommendation system with like a 2-hour buffer in the middle of it, which is not great. I will say, however, that it did actually kind of work out in the sense that we had a real-time recommender system whose failure mode was a non-real-time recommender system. And like the users didn't know we'd roll this out that morning, so they didn't actually notice anything. So in terms of our SLAs and so on, we're all good. So yeah, everyone loves queues. Obviously, we did actually want to fix this. So next morning, kind of pulled up our monitoring, seeing, well, what is the job that is doing this? Obviously, had a pretty good idea. It's this job which is pretty much the last step from the previous slide. So we get our batch predictions that we've computed overnight. We have an API that we can call to get the real-time predictions for a user. Then we combine that data, we serialize it in a specific format, and we put it into another data store. And literally any one of these steps could be the slow step, or all of them, if we're unlucky. So we dug a bit more into our monitoring. So this is a screenshot from AppSignal. Like the really tiny bits that I've kind of circled in red, those are all the API calls and the data stores and so on. So they're clearly not a problem. But there's this really big step here, which is like 90, 95% of it. And that is the serialized step, which I actually didn't really think would be a problem, but clearly it was. And that's handled by this class here, which is conceptually called score map. Conceptually, it's just a wrapper around a hash where the keys are the IDs of the items and the values are how recommended are those items for you. And from the point of view of this job, the main entry point is this serialized method, where we take the data, turn it into an integer array of integers, and pack it in this specific format. And this is just iterating using flat map over the scores. And all we're really doing is we're taking the key value pairs and we're scaling the values so that no matter what the source data looks like, the value is always between 1 and 1,000. That just makes things easier to deal with afterwards. This is the scale factor where we just take the biggest value and divide it through. So I looked at this and thought, well, this seems legit. Clearly it wasn't. So we need something a little bit more refined than that. And we started using Ruby-Prof, which is a profiler. And what that means is that it records the behavior of code, who is calling what and when. And then it uses that to produce a bunch of reports on where your code is spending time. And it's not something you kind of run preemptively. It's more something is slow, someone's shouting at you, and I need to understand why. So here's my Ruby-Prof sort of benchmark script, if you will. I load Ruby-Prof, so just a gem you can install. I load some example data. Sometimes generating the right input that will cause the problem is like half the battle. But in this case, it was fine. Just literally 500 key value pair, randomly generated hash was fine. RubyProf.profile is like the actual profile-y bit of it. So everything that's in that block gets measured. And then once you've got that data out of RubyProf, you need to display it in some way that is readable to you. So that's what this code here does. There's a bunch of output classes that come with RubyProf. I quite like this HTML-based ones, but there are a bunch of other ones. And there are some that produce output that is readable by other tools. And you can make your own classes as well. So I ran all that, and you get kind of this kind of wall of information, which kind of ratio of amount of code on the slide to amount of info is a bit scary. But let's have a closer look at it. So each row in this table is one method. The one at the top is this, well, it's not really a method. It's the block that you pass to RubyProf.profile. It's got a bunch of information there. So kind of on the left, you've got some timing information. So how much time does it take to run this med as a proportion of the total runtime? So for this top level one, it's kind of total. It's 100% kind of by definition. So the next attribute, self, what that is saying, well, yes, you spent 100% of your time running this method, but did you actually spend most of your time running other stuff inside that? Other methods which are elsewhere on this table. And here the answer is yes. This method basically did nothing else other than call some other stuff. And then obviously you have that timing information as numbers of seconds rather than percentages. And on the right you have some call stack information. So this method called these other two methods and it called them once. And it was the only time those methods were called. So that's useful. It doesn't really tell me anything yet. If I look at the next couple of rows, they're kind of the same, that the total time is nearest estimate 100%. The self time is basically 0. This is pretty common. You often have a few layers of kind of wrapper code before you get through to where the time is actually being spent. So what I normally do is I just scroll down the table to the first thing I find which has a self time that's sort of non-trivial, which in this case happens to be the each method on array. I can see that each has been called by a numeral max by. I can see it's calling the abs method on float 250,000 times, which seems somewhat excessive given I told you my input was a 500 key value pair hash. And all these method names are hyperlinked, so I can click on those things to see the same information for that method. And clearly, I'm not saying something wrong with the standard library, so what I need to do is now go back up the call stack until I find some of my code, and why is it calling this in this way? So click around a bit, and we get to the scale factor method. It's been called, it is 98% of the runtime of my code. And it's the thing that's calling max by, which is then calling that kind of whole call chain. So have a look at that method. The first thing that kind of pops out, this method takes no arguments. The scores hash is not one that we mutate, so it's going to return the same thing every single time. So obviously we could just memorize this. But then in terms of understanding why is it taking so long, well, you got your hash scores. I call .values on it. That returns me an array of values. Then I use max by, so that iterates through all the values, calling abs on each one, so I get the biggest one by absolute value. So that block gets called, if I got an input of size n, it gets called n squared times. And n squared is always like bad day. So if I memorize it, then it's still going to call scale factor 487 times, but it's only going to iterate through that array once. So I should be getting rid of 250,000 calls to end abs. And yeah, it did, several hundred times faster. So you might say, well, this is great, being able to see this information. Why don't I just have this running permanently so that whenever I'm curious about something, I can click on my monitoring and see all this data? And basically, it's because it slows stuff down. RubyProf 1.0, which came out relatively recently, is better than the old versions. It's still kind of 3 to 4 times slower, maybe 2.5 times if you're lucky. So it's not something you can really run constantly. And it's also generating a lot of data. And kind of a corollary of that is that it distorts things because it's making your Ruby code 3 or 4 times slower. It's not making your database queries or your API calls or your file I/O any slower. So it's going to exaggerate the importance of your Ruby code. But maybe you're still kind of greedy and you're like, well, can I get some of this insight without this performance penalty and without this kind of distortion? And you can using a thing called a sampling profiler. And basically, the reason why RubyProf has this big overhead is because it's very exact. It's every single method call. It's writing down who called this and keeping track of that. So a lot of method calls happening in a Ruby program, and that's overhead is paying on every single one of those. On the other side, a sampling profiler is approximate. And what it's doing is, as your program runs, maybe once every 100th of a second, it will pause your program and just grab what is the current method. Actually, it grabs the whole call stack, but let's just simplify and say it grabs the name of the current method. And that's all it has to do, and then it can let your program resume running. And then when it gets to the end, it will say, well, which methods did I see and how often? And all it's going to say is that if I saw scale factor as the running method 95% of the time, then I'm going to say scale factor took 95% of the runtime. And the cool thing about this is that you can trade off accuracy versus overhead. So maybe I want to run it once every millisecond instead of once every 100th of a second. It's a bit more overhead, a bit more precision. But you have that control. There is a good sampling profiler for Ruby. It's called Stackprof by Aman Gupta. Pretty straightforward to use. You can Stackprof at run. These are basically the default options. And then whatever is in the block gets measured. The default output looks kind of like this. So there's obviously much less output than you got out of Ruby-Prof. I mean, there are other options, and you can do flame grass and stuff. But it's still much less than Ruby-Prof. But that said, I mean, it has picked out the culprit. If anything, slightly easier than Ruby-Prof, but there's less information to look at. So I said it had less overhead, so I thought I should probably, justify that. So I took my code, I wrote a little script that ran it, so I think 100 times in a loop. Just on its own, took 6 seconds and change. I then ran Ruby-Prof, so no instrumentation. I ran Ruby-Prof on this same benchmarking script, and it took 27 seconds. That's 400 a bit times. It's kind of like a worst case for Ruby-Prof. And then I ran it through Stackprof on the default settings, which is once every millisecond. And yeah, maybe there's some overhead, but it's probably measurement error. So there's basically no overhead for my use case, which is really cool. So you can run this in production if you want. There's even like a rack middleware in Stackprof so that you could hook this into web applications. So just to kind of summarize on my performance problem, use monitoring, people venting at you on Twitter. That's how you can detect problems. They're carbon-based neural nets. They're very sophisticated. Stackprof can actually help you kind of drill that down in production if you need to. I would then recommend kind of extracting into a small benchmark, something that you can really iterate on really quickly. Make a change, run it, and 2 seconds later have the answer, have I made it slower or faster? And if you still need help, then yeah, use Ruby-Prof to kind of dig into that a bit more. And hopefully the next step is profit. So the next thing I want to talk about is memory. I remember being a new Ruby developer coming from C, and this was amazing for many reasons. One of them being, wow, I don't have to worry about memory anymore. This is great. Garbage collection takes care of memory. The Ruby core team takes care of the garbage collector, and I can just worry about my application. I mean, it's certainly true that the core team spends a lot of time on memory and the garbage collection and so on. These are just some of the improvements they've added over the past couple of years, without even naming like just the general performance improvements. But pretty soon, and I'm sorry for anyone who's still in this honeymoon period, yeah, you still have to worry about memory. So if you load a massive file into memory in one go, that's going to ruin your day. If your application has a very large kind of base footprint or use a lot of memory, then that's probably going to impact your hosting costs or your run times because you spend a lot of time garbage collecting. I don't really want to talk about that kind of memory problem. In many ways, that's just a performance problem, but the metric, instead of being time elapsed, is amount of memory allocated or number of allocations. Ruby-Prof has a measurement mode where it will do exactly that. And I know the monitoring system I use, AppSignal, it will tell me how many memory allocations happen on each request. Instead, I want to talk about an error I got through from our monitoring system. It got paged to me one day, which is no memory error, which I'd seen kind of out the Rails console in IRB many times, but never in a page, I guess because if you're out of memory, it's quite difficult to contact a remote server to trigger a page to someone that's halfway around the world. So I was quite curious. It was kind of 10 in the morning, wasn't a busy time for us. So I started looking into our monitoring. And when you look at the kind of lifetime usage of a process, you're kind of hoping for something a bit like this. It starts out growing quite quickly as stuff gets loaded as needed. It ramps up, then it kind of eventually stabilizes. And instead, we were seeing something that's much more like this. It's kind of growing steadily, and there's no kind of end in sight. That means you have a memory leak. Yeah, big font because it's scary. And you might feel betrayed as a new Rubyist with a memory leak. How can this happen? Why is the garbage collector not doing its job? Well, there's a couple of places they come from. So obviously, native extensions. So C code doesn't play by the rules. That's a whole different talk, how to track down leaks in C extensions. But that can definitely happen. And a couple of C extensions have been notorious over the years for leaking memory. But the rest of the time, if you have a memory leak in Ruby, it's because Ruby thinks that you are still using that memory. You may think you're not using it, but Ruby does. So that's often some very long-lived objects, caches that have got out of control, global variables, if you're still using those. And they often boil down to not understanding the life cycle of these objects. You think it's a short-lived object, but it's not. I've got an example here of a memory leak that I wrote once. So this is a rack middleware. I copied this method from a Rails controller, which is kind of a dumb thing to do, as it turned out. So in a Rails controller, Rails creates a new instance for every single request. So the controller object lives for, 100 milliseconds. So this little @things cache, it will have maybe 2 or 3 things in it, and then after 100 milliseconds, the controller object gets destroyed, and this goes with it. A rack middleware is very different. A rack middleware lasts for the entire lifetime of your application. So this thing just grows and grows and grows until it's got the whole of that database table stored in that instance variable, and probably all the associated objects as well. And yeah, in-memory databases are great, but don't build them like this. So yeah, misunderstanding the life cycle of your objects. I said leaks were scary, and I think there's a couple of reasons. The first is that they're a global problem. It's like there is all of the complicated behavior of your application that's kind of drilled down to one number. And it doesn't really give you any clue on where to start. It's not like a user saying, your app is really slow when I press this button. There you know where to start. Or we get a performance alert through for your monitoring saying this endpoint is slow. And again, you know where to start. With a memory leak, it's just, I don't know, something's leaking. Second thing is memory usage is quite complicated and noisy. The patterns around memory usage are very complicated. There's actually a very good blog post recently by Richard Schneeman kind of digging into that. Hi, Richard. So you've got this very complicated behavior, and you're trying to pull out this very small amount of signal. You've got an application that's making, tens of thousands of allocations per request, and there's like 1 of them or 2 of them that are bad. So yeah, it's complicated. Oh yeah, and obviously dependencies. Very easy to update a gem, put in something new, and there's a leak in there. So if you get back to my problem, I've got my leaking Rails application. So the monitoring and so on can't tell me where the leak is coming from straight away, but my first hope was, well, maybe this is a really new leak. Maybe if I'm really lucky since the last deploy, and then I'll just have a very small amount of code to audit. Unfortunately, the answer was at least a year. And it's at least a year because we had 1 year's worth of monitoring data. So you might be thinking, well, how do we not notice this for a year? Which is maybe not the best. Well, it's either a very slow leak or a very rare leak. It was taking about 2 weeks to exhaust memory on the instances that we're using. That's doing about 3 million requests a day. So very gradual. And because it's 2 weeks, we deploy more often than that. Substantially more often than that. And even if we're not deploying, we're starting up new instances to deal with load or stopping them and so on. And so it's very rare for the app, for an individual process to be running long enough for it to be a problem. And if it did become a problem and an instance fails because it's run out of memory, then it gets automatically retired and replaced. And we just say, oh, AWS, what do they know? They are so unreliable. But no, obviously, it was us. So, yeah, restart your apps all the time. Thank you for coming to my talk. In all seriousness, the whole let it crash thing is actually quite a sound idea. But again, that is another talk. And I wanted to fix this leak. The problem I had is I could not reproduce it. So I spent, a day or 2 trying. So I tried, different endpoints in the app. I tried all kinds of tools that, generate synthetic load. But I wasn't getting anywhere. Whatever I did, it seemed like it was not leaking. Or maybe it was leaking so slowly that I couldn't detect it. So what could be happening? Or maybe I'm not just picking the right endpoint. I don't know whether this is a common problem or a very rare problem. Maybe it's some weird endpoint that gets hit, once a day if you do something very specific, and that's where the leak's coming from. Maybe it's a usage pattern thing. Like maybe there's a race condition in a cache somewhere, and the only way you leak is if you reproduce that race condition, and whatever I'm doing locally is not doing that. Or just weird environment differences. That stuff happens. So having kind of exhausted what I could do in sort of our development and staging environments, debugging in production, which sounds like a really bad thing that we should lock the doors so no one can see that we're talking about it. But if you need that insight from production, sometimes you got to do what you got to do. And to be clear, I'm not talking about old school. I'm going to open up a text editor on the server and start editing files, and like in the good old days. I did PHP once. I'm just talking about instrumenting my code in production to get some extra data. So there's two tools I kind of used. First is rbtrace, which is actually another tool by Aman Gupta, the Stackprof. It kind of builds itself as strace for Ruby, and what that means is that you can connect to a Ruby process and get a lot of insight out of it. So you can count method calls and garbage collections, and there's all kind of options kind of filtering down that fire hose to something manageable. You can do back traces, which is really cool. So say you've got a Ruby process that's stuck at 100% CPU, or I don't know, stuck at 0% CPU. You're like, what is this code doing? Well, get a back trace, and you'll see what the call stack looks like on all your threads, and hopefully you can see where that time is going. But the other thing it can do, which what I was actually using it for, is you can inject arbitrary Ruby into a process, which is quite cool. And the thing I wanted to inject is this thing called trace object allocations, which is part of ObjectSpace, so that's in the Ruby standard library. And what that does is it records details about every single memory allocation that happens in your system. And you can dump all that data out. It does come with this warning in the documentation. Note that this feature introduces a huge performance decrease and a huge memory consumption, which kind of makes sense. That is every single allocation. I mean, like Ruby-Prof, where every single method call was incurring overhead, and now it's every single allocation. So my plan was, well, maybe it's bad if you just have this everywhere, but if I run this just on one of our EC2 instances, and I only use rbtrace to turn it on a single process on that instance, well, that's probably only single-digit percentages of our requests. So it's probably fine. And I won't do it like on Black Friday or something. So yeah, do that. This is the danger zone. And then I'll just run this for a couple of minutes, get a heap dump, and then analyze that heap dump offline. And then hopefully profit. So you kind of have this incantation with rbtrace to run it. Kind of the meat of what I'm doing is I just want to trace object allocation start. Let that running go for a couple of minutes, and then trace object allocation stop, so that it stops consuming all the memory and everything. And then just dump that to a file. So I did this a couple of minutes, a few hundred megabytes of output. So you might be wondering, what is in a heap dump? In a way, it's quite simple. It's one JSON object for every single object that's live in your application. And they look a bit like this. So you start off with an address. This is just where in memory was this object. You get a little bit of type information. So this is not type as in your class name. It's like the sort of internal C types. There's about a dozen of them. It's things like object, string, array, and so on. So 99% of the time, if it's something from your code, it's just going to be object. You do have the pointer to the class object for this object. So you could go looking through the heap dump for that address and see what it is. Quite often you don't need to, because the next bit of information is where was this memory allocated. So in this case, it's a Mongo ID document of some sort. You get generation, which is very useful. So every time garbage collection runs, the generation increments by 1. So this is effectively telling you when was this memory allocated. You get some information about the footprint of the app. So it's got 3 instance variables. Mem size is kind of approximate. It works for some things and not for others. So take that with a pinch of salt. If you see 40, it's probably not telling you the whole truth, but that's kind of the default size for a Ruby object in memory, is 40 bytes. And that's like nRuby on the Apple II, which is a lot smaller. References, that's any object is holding on to. So say you had an array, then you'd see all the contents of the array there. Then you get some flag data. So in this case, WB protected is to do with the incremental garbage collection. So this is great. It's very detailed, but there's literally a million of these in this file. So it's not where you want to start. It's far too much detail. So you want to get some aggregate stats out of that. And I used a gem called Heapy, also by Richard Schneeman, who's still there. He hasn't left, so it's good. First thing I thought, well, what does this look like if I have an application that's not leaking? So I give it my heap dumpter file. It grinds away for a couple of seconds. The first thing you see is generation nil. So this is basically all the data for allocations that happened before I turned on allocation tracing. So this is like the lion's share at the start of my app. And I've allocated 475,000 objects. And the memory is 0 again because the tracing wasn't on at that point. These are the first few generations after I turned on tracing. So there's a small amount of memory still being allocated, and it's still being used much later on, which is kind of OK. And then there's 2,000 and something generations for which we have no memory retained. This is what you want. There was memory, it got used, it got released, that's fine. And there is a small amount of memory being used by the most recent generations. That's what my code is currently working on. So this is what you want. So then I ran it on my bad dump. So the first bit is kind of the same. I've got these memory being allocated early on in the application startup, and which is still there. But then I never get this gap. These generations, they've all retained, 10 objects. These ones, they've all retained 10 objects, and just forever and ever. So I picked one of these at random. Have a look, what's in there. First thing you get is you get some information about what you've been leaked. So I've leaked this amount of memory, and this is where it was allocated from. You normally get the full path by truncating them to put on the slide. So I went into the Rails code base to see what this code does, and it's to do with the template compiling. The next thing you get is you get the actual values that were leaked. And this is really cool because for the first time I actually know which bit of the app is leaking because I recognize those view names and I know what code it is. And there's this little outfit display that we embed in partner sites through an iframe. And then I was just curious to see if there's anything else. I went back to the actual heap dump file, and I found this thing. All these objects say uncollectible true, which is probably why they're not being collected. But it doesn't really actually help me that much. Two questions, really. Why are there so many of them? I don't have an infinite number of templates in my app. So there shouldn't be an unexhaustible supply of them being leaked like that. And why is the method name uncollectible? Some of you, may remember that a couple of years ago you did have to be really careful with symbols. Method names eventually get turned into symbols because symbols couldn't be collected. And so if you created symbols from user input, say, then you were opening yourself to memory leaks. But one of the changes in Ruby 2.2 was symbols can be garbage collected. There was actually some small print. Terms and conditions may apply if statutory rights are not affected. There are two kinds of symbols. So there are mortal symbols. So if you run foo.to sim, you get a mortal symbol. They're mortal because they can die, they can be collected. And you get immortal symbols. And these are basically come out of C-level references to stuff. Kind of a rule of thumb for garbage collection improvements in Ruby. It's always the C-level stuff that makes everything horrible and complicated. And symbol garbage collection was no exception. And as it turns out, if you define a method, you get an immortal symbol. So that answers why these things can't be collected. It still doesn't answer why there are so many of them. There is supposed to be template caching. And I was looking at the code that said it was caching these templates. So the first thing I checked was I actually running in production with development settings, which is easily done. But no, it was actually running as it should be. So I kind of dug into the Rails codebase a little bit to understand, remind myself of how this actually works. So every template gets compiled to a method. Every time it does that, even if it's the same template, it generates a random name for it. Well, the prefix is constant, but the suffix, those numbers at the end, are random. So Rails will search multiple folders for your views. This is called the view search path. And conceptually, it's an array of strings, the path that it looks for. In practice, there are these objects called resolvers. Before I looked into this, I kind of imagined the template cache was one great big hash of, paths to methods or something like that. But actually, the caches live inside the resolvers. So if you have 3 paths, you have 3 resolvers and 3 caches. And when you say to Rails, please render me this view, it goes through each resolver saying, please get me this template. And the resolver will either return a compiled template, load it from disk, or say, I don't have this view. So this got me interested in view paths. I started searching around, and I found this code. There's a bit of history here. So this is a before action filter thing. Originally, this iframe that we built for our retailers got embedded into their desktop site. And then one day, they come along, and they want to go mobile first. It was like a couple of years ago. But what they wanted to do is they wanted to run their old site and their new site in parallel so they could A/B test stuff and gradually cut over. So they said, we need to run these two things in parallel. We said, that's fine. We'll give you this query parameter. If you pass it, then we'll render the mobile version. If not, we'll render the old desktop version. And the way we did it is we kept exactly the same views and exactly the same controllers and everything. And some views didn't need any changes. Some views did need some changes. And we pre-painted this view path, which had these kind of view overrides for mobile. And so that allows us to just change out the bits of views that needed changing. So what that looks like in real life is your app starts up, you have these resolvers. So my app maybe just has two search paths, like some views from device, some views from my app. The app starts, all the caches are empty. My app starts getting requests, and fairly quickly, all the templates that I actually use often are cached. Then I get a request for this mobile variant. I've got my pre-planned view path. It adds this new resolver. Obviously, it's new, so it's empty. It renders like it's two templates. So this is like, OK, this is cool. Everything's cached. But that pre-planned view path was in a before action, an instance method. So it only applies to that controller. So at the end of the request, it gets thrown away. So when the next request comes in, we start from scratch again. And so template caching was working, but with a new empty cache on every request, which is not the best. Which kind of boils down to a lifecycle misunderstanding again. Luckily for us, it was relatively simple. This happened we noticed this so long after we'd done the switchover that we could just delete all the old views, although you can deal with it otherwise. So before we deployed this change, this is what our memory use was kind of looking like. And then after we deployed it, just flat. So we were happy. Just kind of summarize. First thing I said, don't be afraid of production. There is a lot of useful insights in there. And there are ways of experimenting relatively safely there. Heap dumps are the bomb. There's so much detail to how your application is using memory. And then the last kind of tip, pay attention to your object lifecycles. Don't assume that this thing that you think is very short-lived is actually very short-lived. That instance variable, you think, oh, it's an instance variable, that's fine. But if the object that it's an instance of is like a class, then that thing will live forever. But yeah, thank you very much.